Hey everyone, welcome back. Today we are unpacking a truly fascinating architectural approach to artificial intelligence, one that honestly completely throws out the rulebook on how machines learn. We're going to be exploring the Prologue Setlin machine, or PDM for short. This explainer is going to completely shift how you think about AI model architecture, performance boundaries, and most importantly, machine learning interpretability. Let's get right into it. So you know the common frustration we all face today, right? Modern neural networks are basically opaque black boxes. We feed massive amounts of data into them, we wait for literally billions of weights to adjust themselves through gradient descent, and then we just hope the output makes sense. But when a deep learning model makes a mistake, pinpointing exactly why it did that is incredibly difficult. But what if we could open that box? What if the logic governing AI decisions was entirely transparent, totally readable, and structurally sound? Well, that brings us to our solution for today, the Prologue Setlin machine. At its core, the PTM is a deterministic, scalar, binary Setlin machine. Now, unlike neural networks that rely on continuous floating point weights, which, let's face it, are essentially giant complex math equations, Setlin machines learn patterns using straightforward and, or, and not gates. Think of it less like a massive math calculator and more like a high-speed sorting system made up of simple true or false logic. And the PTM implementation takes this a whole step further. It gives you exact snapshot replay, and it totally separates the discovery of the rules from the sheer speed of actually executing them. It is transparent, logic-based AI right by design. Here's our game plan for today. We'll start with unlocking transparent AI, then look at Python, C++, and Prolog. After that, we'll hit native speed and CUDA, dive into bounded logic and evolution, and finish up in the interactive control room. All right, Section 1, Unlocking Transparent AI, opening the black box, let's dive into the core philosophy here. If you remember only one single thing from this entire explainer, make it this foundational quote right from the project's documentation. Prolog determines structure, native repeatedly executes it. This is a massive paradigm shift. In traditional AI, the exact same mathematical engine that trains the model is usually the one running the inference, which drags along so much unnecessary overhead. But the PTM philosophy, it completely divorces deliberation from execution. We use a high-level symbolic language to invent and discover the structural rules of the data. And then, and this is the cool part, we compile those discoveries down to bare metal logic gates for blistering inference speed. Moving right along to Section 2, Python, C++, and Prolog, the architecture trinity. Let's look at how this strict separation is actually enforced. So the source material draws some really strict lines in the sand to avoid that usual spaghetti code you see in machine learning frameworks. It spells it out perfectly. Python owns orchestration, reference semantics, and data integration. C++20 owns portable and optimized execution. And GNU Prolog, it is an offline, bounded search participant. Basically, every language is used exclusively for what it does best. Python handles your data sets and the high-level control. C++ handles the raw Boolean logic and memory management, and Prolog acts as the structural brain. It just quietly searches for new rules in the background within really strict limits, stepping in only when a true structural invention is needed. You can really just think of this as the trinity of the PTM. Python orchestrates, C++ executes, Prolog invents. By maintaining these absolute project boundaries, the system ensures that the heavy lifting of logical invention never, ever clogs up the lightning-fast pipeline of per-record inference. Prolog is just completely kept out of the hot inference loop. Okay, Section 3, Native Speed and CUDA, Hardware Acceleration. Speaking of that hot inference loop, let's talk about native speed and how C++ accelerates all this logical evaluation. This right here brilliantly illustrates the power of actually aligning AI with hardware architecture. When evaluating the deterministic scalar baseline, the CPU processed about 460,000 examples per second. Not bad, right? But by simply changing how the data is packed in memory, literally just grouping 64 different examples into a single 64-bit integer, the execution speed absolutely rocketed to over 132 million examples per second. To put that into perspective, that is a staggering 290 times speed multiplier on a standard CPU. And it's all because the C++ engine is utilizing simple bitwise operations rather than heavy floating point math. But what happens when we move things over to the GPU? Well, the data reveals some exact crossover points where CUDA acceleration really takes the lead. Take a consumer RTX 4050 handling high-density rule sets. Handing that off to the CUDA dense bit set backend resulted in a 2 to 2.6 times performance gain over the prior best. Or on cloud hardware like a Tesla T4 dealing with large, sparse clause sets, using a fused vote aggregation improved throughput by up to 1.49 times. So what does this mean for you? It means the system dynamically routes execution to the most efficient hardware path based entirely on the exact shape and density of your specific data. In fact, the CUDA implementation intelligently splits data into 3 distinct backends. Whether you need a sparse grid worker for scattered data or a dense bit set for tightly packed features, the orchestrator automatically chooses the optimal path for you. You don't have to micromanage any of it. The execution just stays blazing fast while automatically using the perfect tool for the job. Which brings us to Section 4, Bounded Logic and Evolution, Inventing New Rules. We've seen the muscle, right? Now let's explore the brain. How does Prolog actually invent structure? What's genuinely fascinating here is how Prolog evolves raw data. It doesn't just stare at flat ones and zeros. Through bounded searches, it performs actual architectural transformations. It can take simple token presence and evolve it into abstract syntax tree, relational encodings. That means it starts to understand not just the isolated data points, but the deep relationships, the paths, and the depths connecting them all. And then, it natively derives those discoveries into compiled binary clauses. It searches for meaning, tests it against a budget, and locks in the absolute best logical explanation. And the results of all that? Well, when the system applied bounded AST relational encoding to a fixed class 2 logic dataset, it achieved a flawless 100% accuracy on both the training and the held-out shadow evaluation rows. It closed the gap completely. This proves without a doubt that bounded symbolic search can find structural, reusable rules that flat traditional pattern matchers just completely miss. So the absolutely crucial point here is this: bounded offline search never interrupts the per-record inference loop. When Prolog finds a new, highly accurate logical rule, that rule is verified in Python, compiled down to native C++ bitwise instructions, and then seamlessly swapped right into the active model. The inference engine just keeps chugging along at hundreds of millions of records per second, completely unaware of the complex symbolic reasoning that actually built its instructions. All right, our final section, Section 5, the interactive control room. Let's move over to the dashboard and see how this all builds into a practical experience you can actually use. The PTM project includes a really slick, dependency-light terminal user interface, or TUI. Think of this as your interactive control room. It's broken down into 5 main panels. You have your hyperparameters to configure your T-Setlin machine, a live training log to monitor diagnostics, inference results to compare your predictions against targets, a dedicated pane to export your model, and finally, a really fascinating clause states window. That last one allows you to literally look inside the brain of the trained model and read its logic in real time. No more black box. The intended workflow here is highly focused and super efficient. First, you adjust your hyperparameters, things like the number of clauses, specificity, and voting thresholds. Next, you hit train. You can test it on the built-in XOR problem. You know, that classic nonlinear logic test that traditionally trips up simpler AI models. Third, you review the accuracy and watch the transparent Boolean clauses adapt right before your eyes. And finally, you export a verified .ptm artifact that is fully ready for production deployment. And I can't stress this enough, this export step is vital. The .ptm artifact is the deployment boundary. Once you export, the training state is completely frozen and lowered into an immutable content-addressed file. It contains the exact logic program, the preprocessing contracts, and the compiled native instructions. You can hand this file over to the standalone PTM-RTC runtime, and it will execute identically, for sure, without needing Python or Prolog ever again. Which brings us full circle to the core takeaway of this entire architecture. Prolog is more expressive during deliberation than the final model is during execution. This asymmetry? It's entirely intentional. We use heavy, expressive, logical reasoning to discover the truth, and then we use lightweight, ultra-optimized native code to apply it. You get all the intelligence of a symbolic reasoning system, but with the raw deployment speed of a compiled C++ binary. It's the best of both worlds. So I'll leave you with this final thought. As the Prolog Tesselin machine continues to evolve, moving us far beyond neural network black boxes and into the realm of transparent, deterministic logic, the tools to understand your data are becoming incredibly sharp. So, what structural discoveries will your data reveal when the AI black box is finally opened? I highly recommend exploring this architecture for yourself. Until next time, stay curious and keep learning.